Hello, we are Group 82 consisting of Chelsey, Elaine, Kritika, Leilah, and Sarah, and we analyze the US residential energy consumption patterns. Why? Because the building industry contributes to 50% of the global energy emissions. The US residential sector has a continuous rising pattern for the energy consumption through the years. Therefore, we are using the residential energy consumption survey dataset from the US NREL with 550,000 data points on residential building location and construction properties, along with the total site energy use. The goal of our project is to understand how building typology varies and to create a model to predict the total normalized site energy. These are our primary research questions. We want to understand which residential home aspects impact energy consumption the most and understand how we can use the building features to model energy consumption. Furthermore, we want to apply these models to make recommendations for improving the energy efficiency of residential buildings.
Our original dataset had over 250 predictors. We first cleaned the dataset to handle missing data and remove any predictors that represented the same information. We then performed an EDA, breaking down our predictors into these 5 categories, and scaled our response variable by the home's square meters to compare homes of different sizes. The geographic predictors revealed that the coldest climate states, particularly northern central states, consume the most energy. With socioeconomic predictors, our main finding was that as income increased, energy use decreased. For building attributes, we saw that as the number of stories increased, total site energy use tended to decrease. For construction material predictors, insulating the walls and ceilings had the largest impact on lowering the mean site energy. And finally, the appliance predictors show that homes with appliances that use fossil fuels have overall increased total site energy use. After inspecting our EDA plots and this NREL plot showing the multicollinearity of features, we removed additional predictors that clearly did not have an impact on total energy consumption. We also manipulated the features via encoding and scaling. Because the majority of our predictors were categorical, we used one hot encoding. The rest of the predictors were ordinally encoded and normalized using the min-max scaler.
Because we had 53 predictors, we started out with a multilinear regression model as our baseline model. Shown here are our top predictors with the largest coefficient values from this model. We found that our model's R-squared values were in the range of 0.38. Another outcome we saw that our R-squared value for the test set was slightly better than our training. This emphasized that we needed to increase the model complexity. So we ran another multilinear regression model and with added interaction terms. Here are the top predictors from this model. Even though the number of predictors increased 6-fold, the train and test scores were still similar. We then moved on to decision tree models, hoping for better performance with our many categorical variables. We started out with cross-validation to find the best depth and landed on 11. Our R-squared values did improve from the linear regression models, and we now have our first signs of overfitting. We finally used a grid search to more accurately tune the decision tree hyperparameters and found the best tree depth to be 12, with a slight improvement in R-squared. In our second phase of models, we moved to ensemble methods that are not as dependent on one specific subset of predictors.
Random forest helps to reduce the variance of the model and decorrelate trees. So based on the optimal depths obtained from the models before, we decided to run a random forest model using depths of 11 and 12. We were also interested in using a much larger depth that would definitely overfit and chose a depth of 20. And with a depth of 12, we had the best results. An additional ensemble learning technique that we tried was boosting, where we fixed the depth of the trees to be 3 and the number of predictors to be 250, only varying the learning rate. But due to limited computing power, we weren't able to test other hyperparameters. As part of the 209 component, we explored a linear tree model, which is a hybrid of linear and decision tree models. But a linear tree model is different from decision trees because they compute linear approximations instead of a constant approximation at each node. When fitting our train data on the linear tree model, we found comparable results to the preceding models, but saw overfitting when using our test data, which can be avoided by using cross-validation. In comparing all of the models, we found that the boosting model with a learning rate of 0.1 resulted in the highest square score.
We then make a case study to apply our model and answer our initial questions. We used a single observation as the baseline and kept all the parameters on the left the same and varied the parameters on the right. We predicted the energy use of 4 upgrades, and in the end, we saw that changing the windows did not help, but improving the insulation of the wall and electrifying the building reduced the energy consumption the most. To conclude, our key takeaway is this. Jokes apart, this roadmap summarizes all of our work. Steps 1 to 3 before training were critical. Then during model selection, we saw that ensemble models performed better than multilinear models, but took more time to train. Our last step included the linear tree model and case study. However, we also encountered many limitations, such as multicollinearity during data handling, or the high dimensionality and extreme coefficients of the multilinear regression. Our next steps include improving feature engineering, diving deeper for each state or climate zone, tuning more model hyperparameters, and using lasso regularization and PCA. Thank you.